In the late 1700s, electricity had mostly appeared as a quick event. A spark jumped, a shock landed, and then it vanished. That briefness limited everything. Experiments depended on chance timing and simple tricks, because there was no dependable source that kept going. Scientists could show that electricity existed, but they struggled to hold it steady long enough to truly test it. Alessandro Volta, an Italian scientist, pushed against that limit. He argued that electricity did not have to be a one-time burst. If two different metals touched, something happened. If a wet layer sat between them, the effect lasted longer. Volta proposed a simple but radical arrangement: stacks of dissimilar metal discs separated by materials soaked in salty water or brine. The idea sounded almost too plain, but the consequence was enormous. Instead of waiting for a spark, a researcher could draw a current that continued as long as the stack held together. Electricity shifted from a moment to a supply. It became something that could be produced on demand, not just witnessed. With that single proposal, sustained current stopped being a dream and started looking like a buildable tool. In 1800, Alessandro Volta moved from idea to proof. He built the Voltaic pile and showed it working, not once, but again and again. That mattered because electricity had been hard to hold on to. Now it came on demand. A stack of different metals, separated by liquid-soaked material, produced a steady push of charge. It was simple, repeatable, and it behaved like a tool. With that tool, experiments changed overnight. Scientists no longer waited for a lucky spark. They turned a battery on and kept it running. That steady current made a new kind of experiment possible: electrolysis. Electricity passed through a liquid and forced it to break apart. Substances that looked stable suddenly separated into their ingredients. The current did not just reveal effects, it caused chemical change. And once chemicals could be split on purpose, new elements could be isolated and studied. The battery became a machine for discovery, not a curiosity. It proved a bold point in plain terms. Stored electricity did work. It could drive reactions, reshape matter, and produce results that could be checked by anyone with the same setup. Electricity stopped being a moment. It became a method. Over the next decades, the battery stopped being a fragile experiment and started becoming a piece of working equipment. Early cells often drifted, weakened, or ate away their own parts as they ran. That made electricity unreliable and messy. Then new, wet designs arrived, and they behaved differently. They produced a steadier flow of current and caused less corrosion. The result sounded simple, but it changed everything. Power lasted. One of the key steps came from John Frederick Daniell, who built a wet cell that delivered a more stable output over time. With steadier current, operators no longer fought the battery all day just to keep it alive. Less maintenance meant longer runs. Longer runs meant new uses made sense. Electricity started moving from benches and demonstrations into regular service. The battery became something you could plan around, not just test and replace. That dependability fit perfectly with the telegraph. Sending signals over distance demanded current that stayed consistent hour after hour, not a surge that faded and forced constant attention. As wet batteries improved, telegraph lines spread and links multiplied. Networks formed, and with them came a new kind of pressure. People needed everyday electrical power, not for discovery, but for routine communication. Electricity started leaving the laboratory and entering daily life. By the mid-1800s, a quiet change reshaped what a battery meant. Until then, most cells behaved like single-use fuel. Once the chemicals were spent, the power faded for good. Lead-acid chemistry challenged that logic. After a discharge, the process could be reversed. The battery did not just run down. it could be charged back up, ready to deliver current again. That one twist changed the math. A battery stopped being a disposable supply and started looking like equipment. You paid for it once, then used it over and over. Electricity became something that could be banked, withdrawn, and banked again. And because charging could happen whenever a generator was available, power no longer had to be used only in the moment it was produced. Rechargeability also solved a practical problem. What happened when the generator stopped or could not travel? Lead-acid batteries offered backup power when lines failed and machines could not afford to go dark. They also made electricity mobile, letting equipment operate away from fixed sources for meaningful periods. The battery shifted from a lab tool into an economic asset, useful wherever reliability and distance mattered. By the late 1800s, rechargeable lead-acid batteries stopped being just something that sat in a station or a back room. They started moving. Engineers took the same chemistry used for backup power and put it on wheels, because cities needed a vehicle that worked without smoke, without steam pressure, and without a horse. The idea sounded simple. Store electricity, then spend it on the road. The battery became the vehicle's fuel tank. Electric carriages appeared in city streets as practical tests of that promise. A motor pulled cleanly from a stop, and the lead-acid pack delivered steady power without constant attention. But the limits showed up fast. Batteries added weight, range stayed short, and recharging took time and planning. Still, those constraints did not end the experiments. They shaped them. Routes got measured in miles, not hours. And infrastructure questions moved from telegraph offices to curbside depots. City transport planners tried electric options where the math worked best. Predictable trips, frequent stops, and regular returns to a base for charging. Lead-acid batteries supported trials that treated electricity like a service, not a novelty. Vehicles that left, worked, came back, and refueled with current. The biggest change was conceptual. Electricity no longer stayed on wires. It travelled, and once power could travel, mobility started to depend on chemistry as much as on engines. In the early 1900s, gasoline cars still asked drivers to do something awkward and risky before every trip. Crank the engine by hand. The crank fought back. If the engine kicked the wrong way, it could wrench an arm, or worse. That single step kept the car from feeling like a simple machine anyone could use. Automobiles existed, but they did not yet feel effortless. Then a different kind of battery job arrived. A lead-acid battery did not need to drive the wheels for miles like the earlier electric cars. It only needed to do one hard burst of work, spin the engine fast enough to start. An electric starter motor took the place of muscle. Starting became a switch-like action. The car became safer, quicker, and far more predictable day to day. That change sounded small, but it shifted everything. With electric starting, the gasoline car stopped demanding strength and constant caution, and it started welcoming ordinary drivers. Manufacturers could sell to more people, more reliably, and at greater scale. The battery, once imagined as the vehicle's main power source, became a quiet enabler instead, supporting a transport system that spread rapidly and soon dominated roads. By the mid-1900s, batteries stopped feeling like specialist equipment and started acting like a household supply. The key shift came from smaller dry cells that could be made in huge numbers, sealed up and sold ready to use. No acid to top up, no careful handling, just buy, install and forget until it ran down. That simplicity turned stored electricity into something ordinary people could trust. Once that trust existed, products changed to match it. Flashlights stopped being emergency tools and became everyday companions because light no longer depended on a wall socket. Portable radios carried news and music to places wires never reached. Battery toys moved and made sound without needing to be plugged in, so play escaped the room with the outlet. A small cell did not just power devices, It reshaped where devices belonged. And then expectations hardened into habit. People reached for a device and assumed it worked wherever they stood, on a porch, in a car, out in the street. Remote controls pushed that idea even further because they demanded power not in one machine, but in the handheld command of it. Convenience became the product. From that point on, being untethered stopped being a bonus. It became the baseline. By the late 20th century, portable electronics hit a wall. People wanted devices that travelled, recharged, and worked for hours, not minutes. But the usual batteries grew bulky fast. Nickel-based rechargeables changed that math. They stored more energy for their weight and handled repeated charging without constant replacement. Suddenly, portable meant something closer to everyday use. Power still mattered, but now it started fitting into the product instead of controlling it. That jump in energy density opened the door to a new kind of machine, the laptop. A computer no longer needed a desk and a power cord to be useful. But the bigger shift came with mobile phones. A phone had to sit in a pocket and still last through a day of calls, standby time, and constant movement between signals. A heavier battery would have killed the idea. Higher density rechargeables kept it alive. Then lithium-ion arrived and the balance tipped again. Compared with earlier rechargeables, it packed even more energy into less weight, and it suited devices that demanded bursts of power without collapsing. That mattered because phones stopped being just phones. They became cameras, music players, and small computers that stayed connected all the time. One change made all of that practical. A battery that carried a day's worth of real computing power. In the 2000s, lithium-ion stopped being just a phone and laptop technology. It scaled up. Companies learned how to link thousands of small cells into one coordinated battery pack, and suddenly the same chemistry that ran pocket gadgets could move a vehicle. That jump changed expectations overnight. Range, acceleration, and everyday usability no longer depended on gasoline. They depended on the battery. But scaling introduced new problems. A battery pack held huge energy in a tight space, and heat and damage could turn a small failure into a dangerous chain reaction. So the 2010s pushed research in a clear direction. Safer designs, smarter control electronics, and better cooling. At the same time, charging had to become quicker and more predictable, and batteries had to survive years of daily use. As electric cars spread, the battery shifted from a nice feature to a national priority. Governments and industries treated it as a tool for cutting oil dependence and lowering emissions because transport burned so much fuel. The battery decided what could be driven, how clean it could be, and how widely it could scale. It became a strategy, not an accessory. By now, the battery had stopped feeling like a component and started acting like a foundation. A smartphone stayed connected all day because a dense pack quietly rationed energy hour by hour. Medical devices depended on the same promise: power that arrived on time, every time, without a wall socket. This reliability changed behavior. People carried information, navigation, and monitoring with them, and expected it to keep working. On roads, batteries pushed beyond individual drivers and into fleets. Electric vans and buses had turned stored electricity into daily logistics, but they also forced new questions about minerals, factories, and shipping routes. A battery no longer came from one place. Lithium, nickel, cobalt, graphite, and copper travelled through long chains of mines, refineries, and assembly lines, and each link created leverage, vulnerability, and political pressure. Then batteries moved to the grid. Large packs absorbed excess solar at noon and released it after sunset, smoothing the swing that once limited renewables. They also reacted in seconds when demand spiked, keeping frequency steady and preventing outages from spreading. But scale sharpened the end-of-life problem. Recycling shifted from an environmental ideal to a strategic need because old cells contained tomorrow's supply.